Well, good morning. You're in my seventh period class. Good afternoon. My name is Mr. Royce. I'll be your AP Calculus AB instructor today. I know I look like Mr. Royce. I'm actually the math teacher that Dr. Frost had back in the 1970s when I taught him the calculus of the space-time continuum. It was my teaching that enabled him to build the time machine. He could come and hang out with you this week. So 1970s calculus teacher. It's a little ahead of the style curve from back then. Let's start out with any questions that you have. What questions do you have on the homework that was due today? I'll take questions on either 2.2a or 2.2b. First question right here. Go ahead.
67.
All right, so we have a question on number 67. Let's see if we can track that one down. Here it is. So just to give you a quick talk through number 67, it said, find k such that the line is tangent to the graph of the given function. So we have a function y equals k over x, and keep in mind that if k is a positive number, then the graph of k over x is going to be that of a hyperbola. It's a hyperbolic graph, and since we want tangent to the graph of the function, we basically have to say, well, I'm going to rewrite the function as kx to the negative 1 so that I can use my derivative shortcut. Using the derivative shortcut, think of k as just a constant, x is a variable. You've got negative kx to the negative 2. So to find the value of k, I set up a system of equations. First of all, such that the line is tangent to the graph of the function. There was a line here that was given. So the negative 3/4 x plus 3 is given. I'm going to put that in red here just because we're generating a picture of what happens. 1, 2, 3 is the intercept. Okay, so we need to pick a value of k for the graph of the blue function, y equals k over x, so that the red line touches this branch. And as you can see, the line y equals negative 3/4 x plus 3 goes through quadrants 2, 1, and 4. Therefore, there's no way that this line will hit this branch here. So that tells you that k is positive. The k you're looking for, you know it's positive. But notice how I take the equation of the hyperbola. This blue graph has two branches. It's two branches of hyperbola. I'm basically setting the blue graph equal to the red graph. That has to be true. They have to be equal to each other. But one other thing has to be true is their derivatives have to equal each other. So in my second equation in the system, I set the derivative of the hyperbola equals the derivative of the line. So why am I doing this? Well, there's really two unknowns. K is unknown, but also the x-coordinate of the point of tangency is also unknown. Otherwise, we'd be able to get away with just one equation and one unknown. Since both k and x are unknown, I set up a system of two equations in two unknowns. So here's my system right here. Now I have to use substitution or some method to solve for k and x. So I solve the first equation for k, I multiply the second equation for k, and then set them equal to each other. Well, once I set them equal to each other, I've eliminated k, and I'm going through it, I'm solving for x. It's like, okay, I haven't found k yet, but I do know the x-coordinate of the point of tangency is 2. Once I know the x-coordinate of the point of tangency is 2, I can pick either of these two equations to solve for k. It looks like I happen to pick this equation right here. I just replaced x with 2 in this equation to find that k is equal to 3. So there it is. I had to end up solving. They didn't tell you to solve a system of two equations and two unknowns. You just kind of like have to come up with that approach on your own. So have I answered your question to your satisfaction?
Yeah.
Basically what I've done is I've talked through the solution. Are there any other questions on the homework? Homework 2.2b that was due today. Yes, go ahead.
Number 67 again. How did you find the
second equation?
Yeah, second equation.
The second equation is based on the idea that the slope of y equals k over x, the slope of the tangent line drawn to y equals k over x, has got to equal to the slope of the line. I mean, look at the wording of the given information. They're telling you we want the line, given in red, to be tangent to the graph of y equals k over x. If they're going to be tangent, then that means at this point, x equals, we discovered later that's at x equals 2. The slope of the blue line has to equal the slope of the red line. So that's the idea that formed the basis of this second equation in the system.
So you didn't find the prime of
The derivative, not the prime, we call it the derivative.
derivative of.
We found the derivative of the line, which is negative 3/4,
Oh,
and the derivative of kx to the negative 1, which is negative kx to the negative 2. Yes?
What happened to the 3 in the derivative? Because that's what confused me.
Well, when you take the derivative of a constant, you get 0.
Oh, okay.
Further questions? Any other questions on the homework that was due today? All right, well, thank you for asking that. My guess is that students in my 7th period class also had a question on number 67. So now let's jump back to this lesson. By the way, the product and quotient rule lesson is going to be the topic for the homework that's due on block day, where it's finally going to get into product and quotient rules. So here we go. Here's where we left off. We left off with number 3 on this particular page. And where are the directions? There's no directions here. If you look at the previous page, you can see the directions are to determine a function for dy dx, and problem 2, determine, find x. The derivative has a value of 0. Okay, so we makes me wonder whether we actually found the solve for x. The derivative has a value of 0. Now that's interesting. Notice how we just blew past these special directions for problem 2. All we did was set up low d high minus high d low, draw the line square below, which, by the way, is the mnemonic device for the product rule. And just in case the students in my 7th period class forgot the chant, when I say go, I'd like all of you here in 4th period to chant out loud and in unison the quotient rule mnemonic device, starting with the word low. On your marks, get set, go.
Low, D high, minus high, D low. Draw the line and square below.
I'm not convinced they were able to hear you, this microphone. I'm not sure how. So this time, let them hear you all the way. All the way into the future. This is like a little time machine. It will take you into my 7th period class. Ready? Go. Low.
D high, minus high, D low. Draw the line and square below.
That's what I'm talking about. Where is he? Is he gone? Is he in the future? No, I'm back. I'm here in the present. Any questions? Yeah, Will, go ahead.
Oh, I don't know a question, sorry.
You have a question?
No, sorry.
We're
I was
just kind of
like,
experiencing the moment.
Yeah.
Yeah, that happens. All right, so here we go. Notice that there were some extra directions here. The derivative has a value of 0. Look, if you had to solve for x when the derivative is 0, this is the part of problem 2 that we just blew past. What you would have to do is ask yourself, well, if y prime is equal to 0, how would I solve for x? Well, if this entire fraction, low d high minus high d low, draw the line square below is equal to 0, that means that which part of the fraction must be equal to 0? The numerator, the denominator, or something else? The numerator's got to be equal to 0. So if you had to solve for x to find the point at which there's a horizontal tangent line, you would have to set up the equation x plus 3 times 2 minus 4e to the x minus 2x plus 4e to the x is equal to 0. And this is the equation you'd have to solve. I'm not saying that'd be easy, but that's the equation you'd have to solve. I'm going to leave it to you to think about how you would actually solve that and whether you would need a calculator. But that's all I'm going to say about number 2. Let's go ahead and go forward to problem 3. Okay. X represents a variable. C is a letter that represents a constant. So you're going to have to keep track of that. Remember how earlier, just a few minutes ago, a student asked a question about finding the derivative of 3 in the line y equals negative 3/4 x plus 3. Well, the derivative of that constant was 0. That's going to come into play whenever you have to find the derivative of c squared. It's going to end up being 0, whereas the derivative of x squared is not 0. So let's find y prime. Setting up the skeleton of the answer. For problem 3, we set up the skeleton. For low, d high minus high, d low. Draw the line and square below. So try your hand at filling in, your hand at attaching flesh, if you will, to those 5 bones. I'm going to pause the camera. We'll see what you come up with. All right, we're back. Here's what you should have come up with for, and oh, by the way, if you're in 7th period, then you can, the live teacher who's present can just hit the space bar up there on the TV, or on the computer that's in the room, and that will pause it so that students have a chance to try this on their own. So anyway, we're back. So when you do low, you just write down x squared minus c squared. D high is just 2x. Low d high minus high is x squared plus c squared. D low is 2x. Draw the line and square below. So here you're distinguishing between 2 different categories: the category of variables, which has one procedure for taking the derivative, and the category of constants. The strategy for taking the derivative of a constant is to always write down 0. Any questions on how to do the initial setup? All right, so I don't want to go any further with that one. This one, number 4, has a product rule within a quotient rule. So the skeleton for number 4 has many more bones. This is a very elaborate problem. Y prime equals, and you're going to have to write small. It's going to be low, and then d high is going to have within it derivative of the first times the second plus first times the derivative of the second. So there's a product rule embedded within the quotient rule. So low d high minus high d low will be pretty straightforward. Draw the line and square below. So having given you the skeleton for number 4, I want you to try to fill in all those sets of parentheses. So if you're in period 7, the teacher there can just press the space bar, let students work on it for about 90 seconds, and then press the space bar again to come back. I'm back. Now, here's what I was hoping you would do on problem 4. Low is x to the 7th plus 8x cubed. D high is derivative of the first, or 5x to the 4th, times the second, which is e to the x, plus first, which is x to the 5th, times the derivative of the second, which is also e to the x. So it's low d high minus high is x to the 5th e to the x. D low, can someone tell me what d low is in this particular case? Raise your hand if you're reasonably sure you know. Yeah, Ethan, go ahead.
7x plus 24x.
Pretty close. It's 7x to the 6th.
Plus 24x to the 2nd.
Yep, plus 24x squared. Draw the line and square below. Below, in this case, means x to the 7th plus 8x cubed. Any questions on how to do the initial setup for problem 4? Okay, I don't see any hands. You know what? Instead of doing this problem, let's go to the next page. I think the next page, it looks something like this, but let's cross off the problem that's there. We're going to use this page to find the derivatives of the things that we need for page 1. Notice on page 1, we have not yet found, we're going to flip back and forth between the first page and the last page. We have not yet filled in the derivatives on page 1 for tangent, cotangent, secant, and cosecant. So let's use the back page of the handout coupled with the quotient rule to derive a formula for the derivative. Just cross off this thing here. And here we go. Let's take a look at f of x equals tangent x. Let's find out what the derivative of tangent x is. We know derivative of sine is cosine. We know the derivative of cosine is negative sine. What's the derivative of tangent x? Well, to discover that, let's rewrite tangent x as a quotient sine x divided by cosine x. And now we're going to set up the quotient rule skeleton for f prime of x using the chant low d high minus high d low, draw the line and square below. So give it a go. Apply the quotient rule to tangent x in the form sine x over cosine x. Let's just leave the camera on. I'm going to tour the room to see what you come up with. I believe you can find the derivative. All right, well, I wonder what's happening. As you try to find the derivative, you're doing low d high, so it's cosine x. The derivative of sine x, can someone remind me what goes here?
Negative.
D high would be positive cosine x. So it's low d high minus high is sine x. D low is negative cosine x, but watch this move. This is for negative cosine x. I'm going to make that subtraction into a plus sign and then write sine x. Okay? That's another way of writing negative sine x, is just sine x with that negative sign is going to come out front and turn that subtraction sign into a plus sign. Draw the line square below, so you get cosine x quantity squared. Hey, that looks familiar. Sine squared x plus cosine squared x, what's that?
1.
That's 1. So this is 1 over cosine squared x. It's secant squared x. Let's take that to page 1 and record it. This is a major finding. From now on, you'll just say, oh yeah, derivative of tangent x is secant squared x. And you won't have to rederive it using the quotient rule. You'll just remember it. Because that's a big shortcut formula. By the way, there is an overarching, well, no, actually, let's just do secant x. See if you can do secant x on your own. Flip back to the last page of the packet and try to use the quotient rule to find the derivative of f of x equals secant x. After you first rewrite secant x as 1 over cosine x. Give it a go. Use the quotient rule. And at this point, 7th period, just press the space bar to pause and then give students about 45 seconds to try this on their own, then press space bar again. All right, we're back. If you did low d high minus high d low, draw the line square below with 1 over cosine x, low would be cosine x, d high is 0. So it's low d high minus high. The derivative of cosine x is negative sine x. Draw the line and square below cosine x squared. We need to simplify this. Upon simplification, 0 times anything is 0. Negative times negative is positive, so we have sine x in the numerator and a pair of cosine x's in the denominator. Instead of cosine squared, I'm going to write this as cosine x times cosine x. And here we can see the simplified version of the derivative of secant x. Sine over cosine is tangent x. 1 over cosine is what? Can somebody help me out? What is secant x? But for the process of, I said process, I should have said purpose. For the purpose of quick recall, when you're thinking of the derivative of secant x, say secant first, because then in your mind it's easy to remember. The derivative with respect to x of secant x is secant x times tangent x. Derivative of secant is secant times tangent. Let's take that to page 1. Flip back to page 1 and let's record this on the bottom so we have page 1 complete. What we just derived is the derivative with respect to x of secant x is secant x times tangent x. And now for an overarching pattern in this table of 2 rows and 3 columns. The top row I'm going to make green and the bottom row will be red. There is a pattern that takes you from the top row to the bottom. The three main trig functions, graphically categorized, are sine, tangent, secant. It's not sine, cosine, tangent. Sine has a graph that looks like a wave. Tangent has a graph that looks like a swoosh. And then secant has a graph that you've seen it. It's the reciprocal of a wave. It looks like this. So graphically categorized, these are the three big trig functions. Their co-functions have derivatives that are always negative with its partner function. So the derivative of cosine is negative sine. Now you could derive it, but I guarantee that when you derive the derivative of cotangent x, it's going to be the same as this. It's going to be negative, and then its co-function cosecant squared of x. Based on that overarching pattern that we see in this table, can someone predict for me what the derivative of cosecant x is without actually taking the time to derive it using the quotient rule? Does everyone think they see the pattern and can predict what this one's going to be? And see, oh, you know, I see on the camera, this is not quite making it into the camera. Let me push it over like that. Okay. Does anyone see the pattern? You can tell me what you think this will be? If so, raise your hand. I'd like to hear from you. All right. Yes, go ahead.
Negative cosecant x times cotangent x.
That's it. I mean, you could take the time to derive it, but really, as long as you just remember the green row, then the red row comes really quickly. It is negative cosecant x, negative cotangent, or negative cosecant x, cotangent x. Okay, so good work on that. Now, we're going to switch gears to the chain rule. And if you're in seventh period, your live substitute, I'm the video substitute, but the live substitute will now be placing the pile of chain rule handouts, on that table by the door. So in seventh period, one person from each group, come and get enough papers for your group. Come and get the paper notes for the chain rule. Fourth period, do the same. Come and get them. Let's jump into the chain rule. Just watch the camera. Don't trip over the camera. Thank you in advance for being so coordinated.
Yeah, walk part of the camera and say hi, Derek. Derek, make a special guest appearance. Seventh period wants to see you. Do it for Marcus and Jack. You will also come. No.
Sorry, Derek.
No one laughs like that at my jokes. It's okay. It's okay. Fine. And now let's move on to the chain rule. Notice on the chain rule, there is a fair bit of review. The opening page on the chain rule is review. And for the sake of time, we're going to fit to height, fit to width. I want to focus during this valuable class time on the new material. So this is a pre-calculus review here on page 1. Turn to page 2. Page 2 is a derivative review. And as you can see, the derivative review takes us all the way down to what we just learned. So I'm going to ask that you, before you come to class on block day, fill in all of page 1 from memory and all of page 2 from memory. And then I will display those answers at the beginning of class on block day. Let's begin with the new material, which is the chain rule over here on page 3. So flip in your chain rule handout to page 3. What rules have we learned for taking derivatives so far? We've learned the rule for taking the derivative of x to the n. It's still over there on the sideboard. The derivative of x to the n, that's first rule. It's called the exponent rule. The derivative of x to the n is n times x to the n minus 1. We've learned the product rule. That's our second rule. The third rule is the quotient rule. And now the fourth one is the chain rule for taking derivatives. And newsflash, the chain rule is used every time you take a derivative. you might be like, whoa, Mr. Royce, we've already been taking derivatives and we didn't know the chain rule. How can you say we use the chain rule every time we take the derivative? Well, you'll find out there's some cases where the chain rule gives us the exact same answer as all the ones we've done so far. You don't need to know the chain rule, and you'll get the same answer as if you do use the chain rule. So, but we're going to be hitting some more complicated problems as indicated by this structure, f of g of x, which is different than f of x times g of x. When we have a composition of functions, that's when the chain rule is really crucial. Now, we have a real-world introduction here. Let's look at this real-world situation, which provides a context for the chain rule. Consider a circular oil slick. Maybe there's an oil tanker out in the Atlantic Ocean and it's just collided with an iceberg. And oil is now tragically spilling into the ocean, killing wildlife. This is not a happy example. A is the area of the oil slick. It can be the sort of thing where here's the point at which the oil slick disaster occurs. And then when we go active inspired preferences, and the tool preferences for where do I start? Let's start at the center. Check this out. This is what's happening to the oil slick in blue. We're going to pick a blue circle, and this is blue oil. And here's the, as time goes on, the slick is growing, growing, growing. This is alarming, especially for the pelicans, which are in the vicinity of the oil slick. They're thinking, how fast do I have to fly to remain above clean water? I don't want to have to land in the oil. That could kill me, is what the pelican is thinking. Or the seagull. Or the killer whale. You know, the killer whale probably wants to have clean water above it. So pelicans above, killer whales below. And when you take a look, it's like, okay, how fast do I have to go to keep clean water above or below? All right, so dAdt is 10. The fact that dAdt is 10 means that every dAdt is 10 square miles per second. Every second, 10 square miles is being added to the area of this slick. It's moving out there. Now, what do you think is going to happen in the real world if we're adding 10 square miles to the oil slick every second? Is it going to go like this, where it's just the oil slick is moving out, the edge is advancing at a constant rate? Or is it going to be the sort of thing in the real world where the oil slick edge is moving out slow at first, but then it speeds up and goes like that? Or is the oil slick going to start out going really fast, and then as time goes on, the advancing edge is going to go slower and slower and slower? Tell your shoulder partner which one it is. Is it constant speed of advancing edge? Is the advancing edge going to increase at a constant rate? At an increasing rate where it's slow at first, and then it speeds up? Or is the edge of the oil slick going to advance at a decreasing rate where it's fast at first, and then as time goes on, it slows down? Constant, increasing, or decreasing? Go ahead and talk now with your shoulder partner.
It's you start fast and then decrease. Yeah. Decrease and increase in size.
Well, it'll start off increasing.
Well, it says the slick is only going to keep increasing, but
Yeah.
the rate at which it is increasing will start off as it will decrease.
Alrighty, raise your hand if you think that the oil slick edge is advancing at a constant rate. Does anyone think it's just advancing at a constant rate? dAdt is a constant. Nobody has their hands up. Raise your hand if you think it's increasing at an increasing rate. It's like it starts, it's going faster. Raise your hand if you think the advancing edge of the oil slick is increasing at a decreasing rate. It's advancing at a decreasing rate. Wow. Almost everyone has their hands up. You know, you're right, because after the first second, we have 10 square miles. And when you add 10 square miles to that rim, then this rim has an area of 10 square miles. And since the radius is bigger every time, the width of the rim gets smaller every time. I just want to exaggerate this a little bit so you can see it. We're going to go circle. Okay, so it's like, suppose that's 10 square miles. Now, in the next second, we have the area of this rim has to be the same as the area of the whole circle. So maybe I'm just approximating, maybe that's where the edge is after 2 seconds. After 3 seconds, it might be somewhere like this. 4 seconds, 5 seconds. So, I mean, that's exaggerated, but the idea is that each rim has an area of 10, and that this central circle has an area of 10. So you're right. Once this oil slick gets to be at a radius of about 100 miles, then it won't be advancing, the edge will not be advancing very quickly at all. It'll just be a narrow rim around the whole, like a 100-mile radius rim to achieve an area of 10 square miles. So your mathematical imagination is in good shape to understand the chain rule. By the way, if you're taking notes on this, you might want to say like t equals 1, t equals 2, 3, 4. Here's t equals 5. And then this is area equals 10. And then delta A, the change in area is 10. So here's a change in area. This rim has an area of 10. Here is a change in area from time 2 to time 3 is delta A equals 10. So that's a way to take notes on this visual dynamic. Okay, now we're going to refer back to that. But again, the answer is not only is it a variable rate, it's a decreasing variable rate. The edge is approaching the pelican at a decreasing rate. It's variable, and on top of that, it's decreasing. Okay, here we go. How do you find a derivative using the chain rule? Okay, now, color coding can be super helpful in this lesson. Super helpful. If you have the capacity to take notes in color, maybe because you're on your Surface, or maybe you have colored pencils or colored markers, imagine how valuable it can be for the people to whom you'll be donating school supplies to this evening at Sunny Acres. Because just like you, many of you have colored pencils and colored pens. Maybe the people to whom you're donating also will want to learn the chain rule in a multicolor setting. So here's the opportunity to empathize with those to whom you will be giving in the hours to come. So here we go. Let's put the X. Let's make that one color. That's X. I'm using green for the X. And we have nested functions here. The output of the G function becomes the input to the F function. And in the center of the nest is an egg. Think of X as the egg. Eyes up here. Some of you are not, the egg, green egg. Green, it's a green egg. It's a green egg. There's no ham. What are you talking about? Ham? Egg? What do eggs, green eggs have to do with ham? Where do you get these ideas?
You got read Dr. Seuss in your life.
Okay, so good question. So now, what color is ham? We'll say ham is red. So we'll make the ham G. I'm going to color not only G, but the parentheses around the egg in red. And then we'll put the green eggs and ham on a blue hot dog bun. So I want you to color F and its parentheses in blue. And green eggs and ham. It sounds like some of you do more than just math. And some of you read books. Is that what you used to read books? Back when you had a life? Okay, so, all right, here we go. The derivative of blue of red of green is found by taking derivatives starting with the outermost nest and working your way into the egg. You start at the outermost nest, work your way. So it's going to be in color-coded fashion, F prime of, so you take the derivative of the outer one, but then you have to be disciplined and rewrite G of, in red, So this is a highly color-coded lesson. F prime of, and now I'm trying to switch over to red. So here we go. G of, and then switch to green for the egg. So the first link in the chain, and there's going to be 3 links, is F prime of G of X. The second link in the chain is to take the derivative of the next innermost function. The derivative of G is G prime of egg. And then the third link in the chain is to take the derivative of the egg with respect to whichever variable is out here. Here, the egg and the variable with respect to which we are taking the derivative are the same variable. So it'll be dx dx. Sometimes it'll be dx dt. And one of the most common mistakes in the chain rule is that students forget the last link in the chain. They forget to take the derivative of the egg. So notice I've color-coded it. It's d egg dx. When I say go, I'd like all of you to say out loud, loud enough for out loud and in unison, I would like you to say, the last link is always d egg d variable. Ready? Go. The last link is always d egg d variable. D egg d variable. In this case, the variable is whichever variable with respect to which we're taking the derivative. In this case, it's x. So see if you can. Now we have to add another color. What if there's 3 nests? The H nest, the G nest, the F nest, and an egg. Color the egg green. H is now the ham. H of. G is now the blue hot dog bun. So it's like G of. Now we have to have some other entity. It's the plastic bag. So F will be, I'm switching the plastic bag in which we keep all the hot dog buns. So F, I'm going to put an orange. Orange, F of in orange. So would you please, and this chain will have four links. Write out all 4 links of the chain rule for this particular problem. So
What
there we go.
d egg d variable mean?
The egg, the variable. Let's, in this case, the egg is x, so dx dx.
Does that just mean like x prime of x?
Well, the derivative of x with respect to x is 1, so in this case, the egg, the variable is 1, but it's not always going to be 1. Believe me, we'll do lots of examples. This is a thick packet. We're going to do lots of examples. Right now, we're just getting the given information down. So go ahead and try this one on your own, and try to color code your answer. The color coding requires dedication to switch from one color to the next many times. But this is fantastic for concept development. The egg is green. Who can tell me what the second link in the chain is? The first link in the chain rule is f prime of g of h of x. Raise your hand if you're willing to tell me the second link in the chain. All right, Tony, go ahead. I know you're just stretching, but technically you did raise your hand. Yes, go ahead. What is the second link in the chain? Say G prime.
G prime.
H of what?
X.
X. That's the second link in the chain. Raise your hand if that's a second link that you came up with for the chain rule. A lot of you did. Any questions on the second link? Okay, each link is we go deeper and deeper, and we start with the outermost nest, work our way in. What is the third link in the chain going to be? Help me out with that, please. Yeah, go ahead. Well,
H prime of x.
yeah. And then, is this the end of the problem?
No.
No. What is the last link in the chain, class?
d egg d variable.
Deg dx. You got the idea. It's the derivative with respect to x of the egg. Now, there's a second version of the chain rule. We have not done any examples of the chain rule with specific functions. We're going to do that at the beginning of class on block day. So this constitutes your introduction to the chain rule. So 7th period, when the bell rings, you are dismissed. The homework is on the syllabus. We'll see you on block day.